All right, we're good. So, I know, that'd be nice, wouldn't it? Maybe. Let me wait till the grades, guys. All grading questions. Give me the time after class, and I'll get all that stuff done, okay?
Will you really stop?
Yes, I'm staying after school and going to the guys. No. All right, so first of all, to go back to rational functions, what I want to do is I want to talk with you guys about, or at least want to go back and review some information that we've previously kind of talked about. So the first one, actually, that ukulele needs to go. So previously we talked about f of x equals 1 over x, and that was actually in chapter 1. We talked about this function. It was actually, I think it was on like your first quiz. It was one of our parent functions, one of the main functions. I told you guys, hey, we need to understand, you guys need to know what this graph looks like. So to kind of just figure out, or just kind of think about what is happening with this graph, rather than create a table, let's just kind of pick some random numbers. So let's pick, 1 over 3. And let's say if x equals 3, or if x equals 6, or what if x equaled 101, or what if x was 999, right? Now the important thing, what happens is the larger and larger my values of x, the smaller and smaller this value gets. Wouldn't you guys agree? Yeah. Right? It's closer and closer it gets to kind of being the value of 0. However, does it actually ever equal 0? Can this ever equal 0? No, right? Or also, could we ever make it negative? If I just keep on getting larger and larger numbers, is it ever going to get to negative? No, it doesn't. What about if we did like a fraction? What if we did like 1/3? Well, again, multiplied by the reciprocal, guys, that's 3, right? If I did 1 over 1/6, that would equal 6. If I did 1 over 101, that would equal 101. So look at these. The smaller my values of x get, the larger the function gets. Okay? And what this does is this produces a curve that looks like this. And again, as I keep on getting smaller and smaller fractions here, is it ever going to, first of all, I can't choose 0, right? I can't put 0 in the denominator because we know that the function is undefined at 0, correct? Yes? So what happens is we have this nice little curve here, and then obviously we can go into negative numbers, but to keep this lecture a little bit short, the curve for the negative numbers is going to look down like this. But the main important thing I want you guys to understand about this function is, one, we have the graph is approaching a horizontal asymptote at 0. It's also approaching a vertical asymptote at 0. So we can just say the vertical asymptote is at x equals 0, and the horizontal asymptote is at y equals 0. All right? And again, we could create a table where you guys could graph it. We could get to that same result there. But that's kind of that's some important things as far as looking at this function, as far as what's going on. We also notice that the graph doesn't cross the x or y axis at all, right? It approaches both of the axes, or axes. Yes, yes. Kind of interesting. All right. So now let's go and further define or further help us with this function by applying some transformations. 1 over x minus h. Whoa, we're doing this stuff again. Oh. And remember, it's the exact same type of stuff. I'm not going to throw in a b because that's just going to mess everything up. Let's just keep it kind of simple. A, same thing, right? That's going to be your vertical stretch or compressed. Doesn't matter if it's going to be vertical stretch or compressed. If a is negative, that's reflecting about the x-axis. H and k, that's the big debate. Is the transformation inside the function or outside the function? Obviously, you guys can see h, the function is 1 over x, so h is inside of it, right? So that's your horizontal transformation. And k is outside of the function, so that's your vertical transformation, right? And again, guys, we did this for square roots, cube roots, quadratics, absolute value. The transformation is all the same. So we can shift this graph any way we want to. Correct? Yes? Yeah. Let's just kind of talk about a couple other things that we talked about. We could say the domain is from negative infinity to 0, union 0 to infinity. We could say the range is negative infinity to 0, union 0 to infinity. Right? Because as you guys look at this, the only values that are undefined for the domain is at 0, right? Because that's when the denominator is 0, which the function will not be defined. And the range, the only time this graph is undefined, looks like it's at when y equals 0. Right? So therefore, the domain and range are the same, at least representation, one's for x values, one's for y values. Let's see. We can see that, I'm not going to write this down, but just so you guys can visualize, the graph is unbounded, correct? Right? It is unbounded. The graph is decreasing when less than 0, decreasing when greater than 0. So the graph is always decreasing. Let's see. The graph is odd, because if you reflected about the y-axis and reflected about the x-axis, you guys can see that it's odd, right? It doesn't have a relative max or min, right? You can see it's unbounded. And here's the other important thing. Let's look at the end behavior. This is kind of a good one just to kind of review as well. Remember end behavior when I gave you guys like crazy functions like this? And we kind of said like, hey, what's happening to the graph, right? And we said, all right, as we're going to the right, right? And we would write this in many different ways. We would say, as the graph is going to the right. We're basically saying, what is the graph doing? Where is it going? And you could say, hey, it's going up. But that was kind of algebra 2, right? So for pre-calculus, we say, hey, it's going towards infinity. And as we go to the left, the graph is going towards negative infinity. But we didn't really say going to the left or going to the right. We would say x, as x approaches infinity, f of x approaches infinity. Or we'd say as x approaches negative infinity, f of x approaches negative infinity, where f of x represents like the y values. So we did talk about this before, but I'm going to bring it back because we're going to talk a little bit about limits today. Yes? So another way that we represent this idea of end behavior or approachment is by using the limit. So basically, this limit or the symbol, we've talked about this, but I'm just kind of doing a quick review because, again, as I mentioned, I'm going to start missing some of you guys because you guys are going to be in all these different tests. We do have a whole, like a little lesson on limits, but I might miss some of you on this. So that's why I figured I'd just kind of cover it a little bit today. So in case you're not here because you're taking some test, you at least have a general idea. So the limit is just basically our way of saying the limit as x approaches infinity of our function, let's call our function f of x. Well, where is the graph approaching? As my x values go towards infinity, so as my x values go towards infinity, where is my graph approaching of f of x? Yeah, it's going to 0, right? Wouldn't you guys agree the graph is going to 0? Over here, it's not going to 0. It's going shooting up, right? It's going to infinity. But for this function f of x, it's going to 0. And I could say that the limit as x approaches negative infinity of f of x is going towards 0. As we go towards negative infinity, the graph is again getting towards 0. Yeah?
It's weird.
It's kind of a little weird. It's a new notation. Once we do the notation on this, you guys will get it a little bit more. Yes?
Does the f of x equal 0 have to be next to the limit?
It's the limit of. It's the limit as x approaches negative infinity of f of x.
So it's the limit, and then it always goes down to f of x, and then like a kind of diagonal to f of x.
Yeah, I mean, it really looks limit as x approaches infinity of f of x. Looks more like that. It's the limit as x approaches infinity. So you always got to have something from there. Just real quick, since we're talking about this and we're on the idea of limits, we could have the limit as x approaches 1, let's say from the right. So what is that little plus? So the 1, now it's saying, well, as my function, sorry, not 1. Let's go to 0. As the function is approaching 0. And the plus means from the right. We could think of it this as like your right hand. So you could basically look at your graph, say your right hand. As the graph is approaching 0 from your right hand, the graph is getting approaching what value? So as the x values are getting closer and closer to 0, the y values are going towards infinity of f of x. Sorry about that. Wrote that. And then we could do the limit as x approaches 0 from the left. Same idea. As I'm getting closer and closer to 0 from the left, negative infinity, of f of x. And then here's the big one. What about this? Limit as x approaches 0. So that means from the left and the right. That's technically what we're looking at. We're looking at a value. We're looking from the left and the right. So as we're approaching of f of x, as the limit as x approaching 0 from f of x, which value is it approaching? 0. Infinity, negative infinity?
0.
Can it approach both?
Yeah. No.
Wait, what? Why can't it?
Because the limit is 0.
No, the limit as x approaches 0 of f of x is, well,
We the plus or minus infinity.
Is that the answer?
Yeah, the limit does not exist. Does not exist.
The one time mean grows is
Guys, the definition of the limit is the value that you are approaching. It's the value that you are approaching. And again, we'll get more in discussion. So if this is a little bit like, what's going on? Don't worry, we'll spend more time on it. But in general, just it's the value you are approaching. And if you're approaching two different areas, you're not approaching really anything at all, right? Yes? I mean, so you got to be approaching you got to be approaching a value. And technically, infinity is not a number 2, right? So you could we could also say that the infinity doesn't exist, but we like to be a little bit more specific. And since it's approaching a physical space, we can say that it's going to infinity. But anyways, let's get on to it. So, quick little review on that. Everybody has written down that they need? You need to take a picture. Okay. No, that's one problem actually. Whew, man, we're almost there. Oh.
Anyone have a charger? iPhone?
I'm B. Does anyone have a Samsung charger?
Who even owns a Samsung?
Jessica.
Jessica.
Oh, yeah, that's right.
I do.
All right. So let's get into. Let's do our first example. So the questions I'm going to ask you guys are the exact same questions I want you guys to do in your homework. So when I assign your homework problems, I don't really care what the directions are in the homework. I just want you to do exactly what we're covering, okay? So your first example is f of x equals 1 over x minus 3 plus 1. What I want you guys to find is the horizontal asymptote, vertical asymptote, x-intercept, y-intercept, domain, the range, and if you can, just go ahead and sketch a graph. Okay? So just give it a sec, just give it a shot, just kind of work on it just for a second, and kind of see where you guys are at with this. That's really weird. Okay. And remember the horizontal asymptote test that we worked on over there is over there to determine the horizontal asymptotes. We practiced that last class period. And also we talked about the vertical asymptote, so you guys can work on that. Yes? There is a degree, actually.
Is it just one?
What's the degree in the numerator?
Yeah, is it just
Well, if it was, x to the 1 is equal to x, but we don't have an x there.
one? Yeah, I know.
So what would be like less than 1? X to the 0, that equals 1. Oh, could work. Right?
Oh, okay. Wait, how's x to the 0 equal 1?
Any number raised to the 0 is equal to 1. And I can go over it, but I don't have time to work on it. I can give you a quick little description after we're done today and show it. But yeah, we can go over it, but let's just to kind of focus on time.
So when you do the coefficients, is it the coefficient of x?
They have to be exactly the same when you're looking at the coefficients. So the powers need to be the same.
I have no idea which
No.
So let's go and take a look at it. First thing, is that what I asked? Oh, I asked for the horizontal asymptote. What is what?
above the minus.
This is the power. Okay. So let's go and finish it up here. So in this example, the first thing I'm asking is for the horizontal asymptote. So we have the horizontal asymptote, and the horizontal asymptote is basically saying we need to compare the degrees of the numerator as well as in the denominator. So when you guys go ahead and take a look at this, we can say that the degree of x is just 1. And we don't have a variable up here, so we could represent that as x to the 0. Because, and truly, x to the 0 is equal to 1. Any term raised to the power of 0 is going to be 1, which I can explain later. But for right now, that's something that's coming from Algebra 2 we'll take. All right? Now, if we want to compare our degrees, we obviously know the degree in the denominator is larger than the degree in the numerator. So I go ahead and look at this, and I can see that it's going to be y equals 0. However, before I actually even get to that, I notice I have some transformations, right? And before I even get caught up on there, usually when I see transformations, I want to write them down. And this is something that I'd probably go off from the start. So we can say x minus 3, that's shifting the graph right 3 units. And this plus 1 means it's going to shift the graph up 1 unit. You guys agree with that, right?
Yes.
So if my horizontal asymptote occurs at 0, but the graph is being shifted up 1, therefore my horizontal asymptote is now at 1. So I can say y equals 1. The vertical asymptote is basically, again, the vertical asymptote is going to be your discontinuity. The value that's going to make your denominator equal to 0. So if we go ahead and take a look at this, we can say that, oh, well, what value makes my denominator equal to 0? We could set it equal to 0 and solve, but I think you guys are pretty well aware that the answer vertical asymptote is x equals 3, right? All right. The x-intercept and the y-intercept. You know what? Actually, to get this, let's graph this. I can graph this actually rather simply, so let's kind of make sense of this. If I was to graph this, here's the parent function. That's 1 over x. And then this function then is that exact same function. But again, what you guys can think about is you can take the vertical and the horizontal asymptotes, which cross at 0, 0, and just shift it 3 units to the right and 1 unit up. 1, 2, 3, up 1 unit. That's like the intersection of my asymptotes. Then I can just kind of do this rough little hyperbola sketch. Actually, it looks like that. Do what again? Well, here's the parent graph. You're good with that. You know the asymptotes occur at 0, 0. The horizontal asymptote and the vertical asymptote of my parent graph, which we just went over, cross at 0, 0. Right? You agree with that? So if I'm shifting the graph 3 units to the right, that means the vertical asymptote is being shifted 3 units to the right. And if I'm shifting 1 unit up, that means the horizontal is being shifted 1 unit up. So now the intersection of the asymptotes occur at the point 3, 1. Now, it's not a point on the graph because those are undefined values, but I can use that at least to help me like move my graph. Yes?
I thought last class we learned that with the horizontal asymptotes, it's the degree of the numerator is greater than the degree of the denominator, and there's no horizontal asymptote.
That's correct. The degree in the numerator is not larger than the degree in the denominator.
Oh. Wait, so wouldn't it be y equals 0 then?
It is. It is y equals 0, but the graph got shifted.
Oh, okay.
Right? So you're right. So you're right. You're just going through this. Now, I want you guys to see this. This is important because at least understanding this general sketch, which we should remember from chapter 1, by at least understanding this general sketch, you guys can see that, oh, there are an x and y intercept, right? So we got to kind of make sense. How do we remember where the x and y intercepts? And again, like transformations, this is something you guys can do for any function that you have. We know that the x-intercepts occur when, yeah, so what value is y? 0, actually. And the y-intercept is when x is equal to 0. Okay? So now we could think of f of x here as like our y. You could think of this as the y-axis instead of the f of x axis. So for my x-intercept, all I'm going to do is just plug 0 in for y. So 0 equals 1 over x minus 3 plus 1. Okay? Now to solve for x, I got to get x off the denominator. But I don't want to multiply, because if I multiply, I have to multiply this 1 times x minus 3. And that's just going to be a little bit more added work. So what I can do is I can subtract 1 on both sides. So now I have negative 1 equals 1 over x minus 3. Now I can get rid of the x minus 3 by multiplication. So I'll multiply by an x minus 3 on the top and bottom. Please note, guys, distributive property here. That's why I put that in parentheses. So therefore, this is a negative x plus 3 equals 1. And then you could subtract a 3. Negative x equals negative 2. Divide by negative 1. Divide by negative 1. The x-intercept is at x equals 2. Does that look like it crosses at x equals 2?
Why is it x, not y?
The function. I just set the function equal to this. I replaced y equals 0.
Okay.
So I took the y coordinate, which is f of x, and set that equal to 0.
So it would just be x.
Yeah, you're solving for x, which is the x coordinate, right? Here's the y-intercept. Look at it right there. X equals 2. Right? Yes? No? Maybe so? Okay. Now, we can write the x-coordinate as x equals 2, or we could write it as a coordinate point, 2, 0. All right. Now let's go and take a look at, Johnny, are you okay? I guess I should remember this when you write that email later talking about your grade. Then I can say, hey, remember that one time. That's interesting. Okay. Let's go and talk about your y-intercept. The y-intercept then is when x equals 0. So all you're simply going to do is, let's just use this with y. Now you're going to set x equals 0. 1 over 0 minus 3 plus 1. Y equals, could I write the negative in front, or should I leave it in the denominator?
No.
Should I write it up top? Can I do that? Can you just take it from the bottom to the top?
Yes.
Well, I don't know. Let's see. Because negative 4 over 2 equal to 4 over negative 2, which is equal to negative 4 over 2. Are those all equal? Oh, they are. So I can actually take this negative and just put it in front. And then can I just rewrite 1 and use it as 3 over 3? Or should I use it as 4 over 4? 3 over 3, right? And 4 over 4, you don't want to do that. You want to do 3 over 3, so then therefore you have common denominators. So y equals 2/3. So my y-intercept is at 0, 2/3. And does that kind of make a little sense? Does that kind of look like 2/3 maybe? I mean, roughly. If we had a negative, we would probably want to look at, uh-oh, I did something wrong, right, Douglas? Right? You've got to be careful with that. So by at least understanding the sketching, guys, you can kind of understand a little bit more of where you're going with this. Let's go and take a look at la domain. And so for the domain, we just know that, well, the only discontinuity, guys, is an asymptote, which is at 3. So my domain is from negative infinity to 3, union 3 to infinity. We spent all class period doing that, so that should be something that's quick. The range, same thing. We're looking at the set of y values. Well, it's unbounded, so it's going down to negative infinity. It's going up to infinity. But we have this horizontal asymptote. The graph does not cross. And we can see that from the graph. So therefore, this one is negative infinity to positive 1, union 1 to infinity. I already sketched the rough graph. So that's basically what I would expect you guys to be able to do.
Wait, what? How'd you do the domain and range again?
I'm just looking at the graph. The domain is the set of all x values except for where the graph is undefined. This graph is undefined at the value 3. The graph continues going to the left to infinity, negative infinity, continues going to the right to infinity. The only time it's undefined is at 3. So it's from negative infinity to 3, jump over the asymptote, 3 to infinity. Remember, the parentheses means it's undefined. And you just do the range, same thing. It's just vertical instead of horizontal. Huh? Yeah,
Do the range
asymptotes.
where you jump. So it goes from negative infinity to 1, and then, but if you jump, you'd have to go like all the way.
You're just going over that exact value. Like, for instance, 2.999999999 is in the domain. 3.00000000001 is in the domain. It's just the exact value of 3 that's not in the domain. That's why we use it. It's going towards 3, but exact number 3 is not defined. Yes, we were going to do another example. All right, let's do another one.
Wait, let me at least take a picture.
All right, well, let me write down the right new problem. F of x equals 3x minus 2 over x minus 1. Yes?
Can there ever be like a decimal? The asymptote or the
Mm-hmm. Well, I mean, if it was an asymptote, it'd be one of those, a decimal like transformation, but yeah. All right, so I'll leave it up there, I guess, while some people write it down. So as you're finishing down, for those of you that already have it written down, new function, same questions, horizontal asymptote, vertical asymptotes, x-intercept, y-intercept, domain, range, and then maybe see if we can sketch a graph. I don't know. Is it possible to sketch a graph on that? What? A B.
Is that what that is?
No. Because, well, it's not. This isn't a reciprocal function the way it's written, right?
Do you have like a good order that we should do these in?
Yeah, the way I read them on the board.
Okay.
John, I already talked about that. Yes.
So could you simplify, like for the future, could you simplify and then graph the simplified version, or do you have to graph the original?
No, you can simplify it.
Okay, so you can graph it from the
Sure. Yep. No. All right, this is actually the last one I'm going to do on this stream, and then I'll end the stream, and then that will allow me to give you guys a little bit more time to work on the last two problems we're going to do, okay? But I'm just going to jump into this one just to kind of show you two other things that we can work on. So when looking at this, we have fx equals 3x minus 2x minus 1. So again, it's asking for the asymptotes, right? So horizontal asymptote. And the reason why I chose horizontal asymptote first is just because it typically leaves the least amount of math. We got to compare the degrees. Oh, and here they're both 1. Okay, right? So that's easy. So we go and look at our horizontal asymptote. Okay, so when the powers are exactly the same, or the degrees are exactly the same for each polynomial, you just take the leading coefficient over the leading coefficient. So the leading coefficient of this exponent is 3. The leading coefficient of this one is 1. So therefore, we can say the horizontal asymptote is y equals 3 over 1. Now again, do we know what the transformations are, though, of anything? Do we really even know what this graph looks like? Yeah, it's just going to be 3. That's right. So y equals 3. But we don't really, but for right now, let's just kind of focus down on that, and then we'll kind of see, maybe we'll look at this graph and see if we can maybe sketch the graph and verify that, right? Vertical asymptote is when the function is undefined. So we look at this, and, well, it's undefined and it's not a hole. And we practiced finding holes last class period. So can we factor or do anything like that to eliminate the x minus 1s? Okay, what do you want to factor? No. Can't really factor anything, right? That's kind of a simplified form. But you do want to look for that. You do want to say, hey, could I simplify this and maybe, is it a hole? Because wouldn't that be a great question to give you a hole instead of an asymptote? I think you guys have already been asked that on chapter 1, right? But again, that's something to come up. But this is an asymptote. It cannot be factored out. And we could set equals 0 to say x equals 1. All right, x-intercept. Again, well, for the vertical asymptote is when the function is undefined, right? So it's only when the denominator equals 0. We don't really care when the numerator is equal to 0, right? At least for defining the vertical asymptote. But let's look at, we do care actually when the numerator is equal to 0, and I'll kind of talk about that here in a second. Let's get into x-intercept is when y equals 0. So let's just replace that with y for a second, and let's do 0 equals 3x minus 2 all over x minus 1. Ooh, solve for x. X is in the numerator and the denominator. We don't like x in the denominator, so we need to get it off the denominator, right? So we should multiply it by x minus 1 times x minus 1. Ah, interesting. X minus 1 times 0 is 0. Wait a minute. So, this is interesting. Okay. Does it really matter what is in my denominator? If I'm going to always just multiply it on both sides and I'm always going to multiply it by 0, couldn't we maybe simplify this and just say the x-intercept is basically when the numerator is set equal to 0? Yeah. So denominator set equal to 0 gives you a vertical asymptote. Numerator set equal to 0 is actually going to give you your x-intercept. That's kind of cool. Yeah. It doesn't matter what this is. This could be x to the 5th power. I'm multiplying it by both sides. So to find the x-intercept, it's just the numerator set equal to 0, right? It doesn't matter what function is in here. If I'm trying to find the x-intercept, I really just need to take the numerator set equal to 0. Now, if you want to do the math, go for it. I mean, I'm showing you the math, right? I mean, multiply both sides. But again, you're always multiplying by 0, so, it's a little bit of a trick to help you guys speed it up. Add 2, divide by 3, x equals 2/3, right? We can write the x-intercept. I wrote it as a point last time, right? We'll keep it as points. 2/3 comma 0. Y-intercept. X is equal to 0. Again, let's try to simplify this process. Anytime there is a variable, I'm just replacing it with 0, right? So once you guys say that it doesn't matter what I'm multiplying my x by, I could multiply x by 17, and I could take x and cube it. But would that really change if I plug in a 0? It doesn't really matter, right? So in reality, if I just want to find the y-intercepts, I'm just taking the constant over the constant, right? Because 0 is going to eliminate everything else that's happening there. So I could do this a little bit quicker, too, and just say it's negative 2 over 1, which is obviously equal to negative 2 over negative 1, which is equal to 2. So the y-intercept is 0, comma 2. Ooh. Cool. All right. So the domain is obviously we don't have a hole. We only have one undefined value. So that's going to be kind of rather simple. The function is only undefined at 1, correct? It's only undefined at 1. So my domain is negative infinity to 1, union 1 to infinity. All right. We're going to graph in just a second because I really don't know what the range is. Now, I could say the range is all real numbers except for 3, but we really don't know what this graph looks like, correct? I'm going to show you. So I'll let you guys, I mean, obviously on a EOC, you guys are going to have your calculator, right? And this would take 2 seconds to plug this into your calculator, to graph it, and then you could verify all of your work here anyways. However, honestly, like on a non-calculator portion, though, we don't want to always assume the horizontal asymptote because it actually is possible for the graph to cross a horizontal asymptote, right? The horizontal asymptote is just where the graph approaches because that's what I said, an asymptote. An asymptote is where the graph approaches. The vertical asymptote is undefined. Horizontal asymptote is not always an undefined value for the range. So we'll get to those problems later. But for right now, let's just try to see how could I graph this. Well, some people mentioned, I'm going to erase this work. Some people mentioned some things. Could we simplify this? That's actually a really good way to think about it because right now, there's really nothing. The only thing we've learned is to graph reciprocals, right? So is it possible to to divide this into this?
No.
Oh, well, did you guys try it? You guys just assumed?
I see.
No, why did I say you can?
You said we can.
You learned how to divide using this method.
I hate that method.
Why don't we just try it and see what happens? Who knows? Maybe we'll get the answer. I don't know. So remember, long division. Take the first term in your divisor. Make sure you're take the first. Now you could do synthetic division in this one because your divisor is linear. Remember that? Remember the good old synthetic division? But anyways, let's keep with long division because this really isn't that difficult. You take the x, you take the first term, divide it into your first term of your dividend. X divides into 3x 3 times. Take your 3, multiply it by both terms. 3 times x is 3x. 3 times negative 1 is negative 3. Remember, you put them around parentheses and subtract them. So 3x minus 3x is just 0. Negative 2x minus a negative turns to positive, so therefore that turns into a 1. Negative 2 minus negative 3. Minusing a negative turns it into an addition problem, which is just positive 1. Right? You're subtracting the negative direction. It's your values. So then we get 1. Does x divide into 1? No, so that's your remainder. So we add the remainder, and then do you remember what we did with that after that?
Over x minus.
Yeah, over your divisor. Whoa, wait a minute. Look what happened. By dividing it, I just rewrote it, f of x as 1 over x minus 1 plus 3. Hey, that's kind of like the reciprocal function, right, that we just did. And let's compare. Do we have a vertical asymptote at 1? Yes. Do we have a horizontal asymptote that's at 0 but got shifted up 3? Yes. X-intercept, y-intercept, we can redo the work if we wanted to, but we're not going to. And then the range, we could say, okay, I know what this graph looks like, right? I can confirm that the horizontal asymptote is not a defined value for the range. So the range is from negative infinity to my asymptote at 3.
How would you know that? How can you just look at it and know the range?
Because I already know what this graph looks like,
Oh, because it's
right? Because it's the graph we just did,
No,
right?
it's not. No, we did 1 over x minus
Okay,
3
yeah, but
plus
this one shifted up 1, up 3.
Mr.
McLogan, yes.
Why don't we just do that as the first step?
We could have. I did it for instructional purposes.
Question, why did you put the +3 at the end instead of the beginning?
I mean, you could keep it in front. Doesn't really matter.
Then that'd be A.
No, A is product. It'd be A times 1 over x. Right. All right. I will end on that. But no, the reason why I brought that up to you is for you to explain that. And then, but also, I mean,